Hi, everyone. Thank you very much for coming to my talk today. My name is Shannon Hicks-Jalali. I'm a researcher in Environment Climate Change Canada. And today I'm going to be talking to you about my work on diurnal water vapor cycles using ground-based measurements to compare with ERA 5 and the Environment and Climate Change Canada NWP model. Diurnal water vapor cycles are of two major components: the 24-hour diurnal cycle, which most of us are familiar with, and then there's also a 12-hour or semi-diurnal component that I'll also be talking about today. The diurnal water vapor cycle we know is a critical component of the larger hydrological cycle. Unfortunately, there are very few measurements of it in the Canadian Arctic and almost no height-resolved studies done worldwide, mostly because there just hasn't been the instrumentation in order to facilitate these kinds of studies. We do know that diurnal cycles are dependent on multiple processes, which makes them useful tools for model verification. And models do need to be verified, because we also know that models have trouble typically representing diurnal cycles, as these are one of the hardest processes to model currently. But we do know that also improving these diurnal cycles leads to forecasting and reanalysis improvements on mesoscale and larger scale processes. The study that we've done is conducted in Iqaluit, Nunavut. It's represented by this red pin here, at 63.75 degrees north, so just south of the Arctic Circle. So we still do have a day-night cycle for the entire year. In the summer, we've had to actually redefine our seasons. So summer here, instead of the typical June, July, August that you would normally see, is now April through September. And that's just because that's the season where we have the most amount of daylight available. Spring and fall, we've redefined as transition seasons be from February through March and September through November, and they have pretty much equal day and night. And then in the winter, we have our least amount of daylight from November through February. We have four main data sets that we use in this study. The first one is the ERA 5 reanalysis, which most of us are familiar with. The second is the Iqaluit GPS, and then it's co-located with our Vaisala dial instrument, and then the GEM HRDPS NWP model, and that's Environment Canada's NWP model. So ERA 5 provides specific mixing rate, specific humidity on 37 pressure levels, but because we're working with instruments here that are on altitude profiles, we've actually interpolated the data onto a 200-meter resolution. The GPS measurements are provided to us by the Nevada Geodetic Laboratory, and those are freely available for anybody. And those provide us with the total column or whole atmosphere water vapor amounts in millimeters. And while they do provide them at a resolution of 5 minutes, because we're working with models that are on an hourly scale, we do average them to an hour. The main instrument that we're working with here that many of you may not be familiar with is the water vapor differential absorption lidar. And that's shown here down at the bottom. It's about the same size as ceilometer, if you're familiar with those. And it provides mass mixing ratio profiles up to 3 kilometers, but because we're working in the Arctic where it is fairly dry, we typically only get up to about 1.5. And it provides a profile of the mass mixing ratio every 20 minutes or so. We have data from the instrument from September 2018 on to June 2020, and so that's what we're comparing with for this study. And then lastly is our GEM HRDPS model, which is the high resolution model at 2.5 kilometers, also providing specific humidity profiles. But because it is a forecast model, we have an initialization time where the model is started. In this case, we're using the 0600 UTC, just because we wanted to avoid assimilating the radiosondes and any uncertainties associated with that. And then we have a 48 hours of forecast afterwards. And similar to ERA 5, we do interpolate the GEM profiles to an altitude grid. If we look at the profiles on average between dial, ERA 5, and GEM, so dial is represented here as the X's, and ERA 5 and GEM are the green and blue profiles, respectively, for mixing ratio, we see that they do agree quite well. There is one region down here that I should point out between 250 and 450 meters. And that region, we do know that there is some solar noise contamination in the dial instrument, so we don't use it. But for the rest of the profile, they do agree very well. A slight difference above here, and that's mostly just because of the difference in the number of profiles between the data sets, and they have an average bias of around 0.1 grams per kilogram, which is quite good, all things considered. And though this is a systematic bias, so this doesn't influence our diurnal cycles, which are a relative calculation. So if we now go look at our diurnal water vapor cycles, which are the altitude cycles are on the top here for ERA5, dial, and GEM. And then on the bottom, we're looking at comparing the integrated water vapor, or the total column water vapor cycles between ERA5, the GPS, and GEM. In the altitude or height resolve cycles, the red regions are regions where we have increasing mixing ratios. Blue regions are where we have decreasing mixing ratios. So if you were to take a cross section across here, it would look something like this that you see on the integrated water vapor. And we can see in the first couple 100 meters or so, ERA5, dial, and GEM agree quite well in magnitude. GEM is slightly higher in amplitude or magnitude, closer to the surface, but comparable. We do see some difference in timing in the phases. But the big difference here when we go above 800 meters is we see the dial has significant amount of structure above 800 meters, and that's because of contributions from the 12-hour component that we don't see in ERA5 and GEM. And this is something that we observe across all seasons for the most part. And we just chose the spring here as an example because it was representative of most of the other seasons. And if we look at the GPS as well, we can see that the GPS also observes a 12-hour component, which is this blue line, blue dashed line. The total diurnal cycle is this black line here. It's the combination of both the 24-hour plus the 12-hour. And we see that the 12-hour component is this main component here. But we don't see that in either ERA5 or GEM's total cycles, and we see that the amplitude of the semi-diurnal cycle in both of them is quite small. And like I said, this is something that we do see across all seasons. So when we look at our across all seasons, we see that the diurnal cycle amplitudes with altitude do have some biases with respect to the dial when we look at GEM and ERA5 across all seasons. The dashed line here in the center is 0. So if we look at the bias for ERA5 and the dial, which are the blue ones, we can see that typically across all seasons, the bias is the ERA5 has amplitudes that are less than the dial observes. Same for GEM, which is the red profiles. We see that typically GEM has amplitudes that are smaller than whatever is observed by the dial, with the exception of closer to the surface in the first 100 meters, like we saw before. GEM's amplitudes are slightly larger than the dials. This is when we look at the S2 component or the semi-diurnal component, we see similar behavior where amplitudes in the models are smaller than the amplitudes observed by the dial. And one other thing that we looked at here is we looked at the change in the solution in GEM with lead time and how stable it was with the changing forecast. And we saw that, which is represented by the standard deviation or the shading around each of these profiles, and they're actually fairly small, which tells us that the solution is fairly stable across all lead times, so that GEM wasn't preferentially, the solutions weren't dependent on the forecast time. Finally, we can look at the integrative water vapor seasonal comparison, similar to like we did before. The GPS is represented by the X's, where ERA5 are the triangle and circles. And with the exception of the summer, essentially what we see is that the amplitudes in the GPS are larger than the amplitudes in the model across pretty much all of the seasons for both the 24-hour up top and the 12-hour component on the bottom. So what are some possible causes for these differences between the observations and the models? Well, we do know that generally higher resolution models are better at resolving diurnal cycles. GEM did perform slightly better than ERA5. We do know that both of the models have a problem where they don't have too many observations informing the model humidity profiles for assimilation. Satellites radius on an aircraft have fairly inconsistent coverage for a given location, which is really what you need to get good high-resolution diurnal cycle measurements. And we saw that surface measurements generally performed better, surface diurnal cycles in the models were generally better compared to the measurements and observations. So, and they have to have typically better temporal coverage, which might be one reason why they had better agreement. Both of the grid points in GEM and ERA5 are mixed land and water, so there may be some more complicated physics that is not being represented there. And then it's possible that the GEM's first 100 meters, where we saw that they had slightly excess water vapor and higher amplitudes compared to the dial, could be due to some excess evapotranspiration there. So in conclusion, both models typically do better below 1 kilometer, where the 24-hour component is the main component. Above 1 kilometer, though, where the 12-hour component becomes more prominent within the dial observations, is where we start to see bigger differences between the models and the observations. In general, the amplitudes of the diurnal cycles are lower than what was observed by the dial and the GPS, with the exception of what we said before, where in GEM, closer to the surface, but in the 100 meters, it's a little bit higher, or in the summer, we do have some higher amplitudes compared to the dial and the GPS. The main takeaway here, though, is that ERA5 and GEM have seem to be missing the S2 components. The S2 components are consistently smaller than both what's observed in the dial and the GPS. That may indicate that there's some missing or complete process in the models. We've submitted a manuscript to QJRMS, and we'd be happy if you went and checked it out when it's published. If you'd like to check out the results from our previous paper, this is the link down below, and I'm happy to answer any questions. Thank you very much for your time.
So thank you, Shannon. Are there any questions for her? Yes.
Yes, thanks for the talk. I'm very curious to learn what's the possible cause of this 12-hourly circulation. Is that related to atmospheric tides, or that's the only thing that comes to my mind, at least?
That's a very good question. I hope you can hear me. We're honestly not quite sure. We know it's expected. It's been observed across multiple studies, but we haven't been able to pinpoint the exact mechanism for the 12-hour cycle. And that's something that needs ongoing research.